Welcome back to the channel. This is another video in our Python for Forensic Chemists data series. And this is an interesting one because it's really the culmination of a lot of the previous videos where we have done data preprocessing of NIR data. We've tried to understand the metadata associated with the analytical data, as well as looking at hotel T squared, building predictive models. And now we're going to take a small pivot into how we can take what we've learned about the lab data, which is everything we've looked at so far, and use that to help us understand how we can make in situ chemical measurements. And this is really how we can now make those sorts of measurements around understanding cocaine or other drugs of abuse or explosives outside of the lab, but leverage what we've learned from high quality in-lab measurements. And so let's get started. Here is our notebook that we have looked at over the past several videos. And now we're in part 1.7. And I've done a lot of the coding already because there's a lot I want to demonstrate and explain and allow you to see the code as it's there. And so the emphasis here is comparing our in-lab results to our in-situ measurements, and I'll highlight some of the trade-offs when it comes to that sort of analysis. But first, recall that if we look at the full article, there's one figure I particularly want to highlight, and that's the one on the screen now. And here we have the entire analytical data set that's included as part of this publication. And so far, we've been looking at this ASD Lab Spec 4 data, which covers 350 to 2500 nanometers. So the visible range all the way to the infrared range. And this is a high quality lab-based measurement. This is the type of instrument you would never take outside the lab. However, we have several other near-IR spectrometers that we might want to take outside the lab one day. This SCiO, MicroNIR, NIR1, and SciWare NeoSpectra are all portable NIR devices that are meant to allow for in situ or in field performance. And so let's take a look at this and we can begin to understand the trade-offs when you have a smaller device which covers a much narrower wavelength range compared to a full lab scale device. And so the way we're going to make this comparison is that we're going to take a subset of the ASD data, build a model, and then fit that model to our respective IR sources. So it's going to look different because each instrument has a different wavelength range. And so we're going to slice that out, build the model, and overlay the results from these various instruments. So let's go back to our notebook. So I have imported a couple additional libraries. All the other libraries we need are already imported from the previous notebooks, but here we need distance, widgets, and OS, and I'll explain these as we get to them. Additionally, I built a few functions to help us in the data processing. Again, this apply SNV is a function of this transformation that we made in video, I think 2, but I've created this function to allow us to more easily apply that. And then I have this convert calls function, which just takes our score data frame and improve the column names for clarity. So let's run that. We don't really need those anymore. And what I'm doing here is using the OS library and using the listdir method, looking in this data files average per sample and looking for the data set from all these instruments, which will be files that start with the letter K, the capital letter K. And I will get this variable called flist. If we look at the output, we have this list here, which are all those instruments I've just shown you, with ASD being that lab-based instrument. The reason I did that is because I want to create a widget that allows me to more rapidly switch between the various data sets, and then I can run this set up this part of the notebook again. And so what I have in the next cell is a way to actually scroll through all the instruments. And so I can actually pass this variable fname into a Python reader. And so if I demonstrate how we do that, if I look at fname.value, we see that we have this matching output by returning the value attribute of this. And so as fname is updated, this widget is updated, fname is also updated, and thus we can pass that forward into our file reader. And so to keep this somewhat simple, I'm going to just be looking at 2 data sets at the same time. One data set called other, which would be the portable instruments, and then the other data set called labdf, which will always be that ASD sample, which is now hard coded here, but that fname value is encoded as part of our f string and will update the path and thus our other df. We could apply our SNV at this step here, but I've chosen not to just for simplicity, but did want to show you that there is a way that we could process a little bit earlier but the processing actually becomes a little bit easier if we wait one step. And so after this, we have two data frames when we run this, and one data frame is other DF. And if we look at the head, we see that we have our NeoSpectra. And let's start with SCiO. I think the difference is way more obvious. And for SCiO, we have our wavelength range between 740 and 1070. And then we've added this extra column called instrument, and we've set that to other. On the other hand, we have a second data frame called lab DF. This is the data frame we've been looking at the entire time. And this has that full bandwidth between 350 nanometers all the way to 2500 nanometers with this new instrument column called lab. This is our lab instrument. And again, the whole point is to be able to compare these two. So we're going to be concatenating lab DF and other DF by looking at the more restricted wavelength window of the other data frame or the portable instrument. So in the next cell, we perform this concatenation, and then we drop the columns where there is no data for one of our variables. And so now all data looks like this. Although the lab data frame has the full bandwidth, when we perform this concatenation of lab DF and other DF, we are now only looking at a subset of our data. If we ignore the drop and run this again, you see how for the bottom set of our samples, there are a number of components where we don't have any variables. And this again is because that data does not exist. So this is how we get around that. And now we have a complete data set where we have our lab data on the top and our other data, our field instrument on the bottom. And now we can perform our analysis. And so in the next step, I'm creating a couple different data frames. And so if you were walking through this, which this data is publicly available, if you look at some of the early videos, I demonstrate how you can access this data. This slide allows you to play with a number of different permutations. And so if you want to explore this differently, I have X, which is all of the data that is numeric. So that's the analytical data, ignoring this instrument column. Y is the instrument column, which we're really just using for data viz purposes. And then in the case where you want to just build a training algorithm off of just the lab data, we're now just querying and subsetting just the lab variables. And for our X test would be just the other data. And so if we were building models based on in-lab measurements and then wanting to deploy those models, this is one way you could design an experiment. And then of course we have our own Y train and Y test, where we are just now taking the instrument columns, but using that same query string to allow us to filter the data. And then here is where you could apply the SNV method to clean up some of the data. And so this is just one way where you can build your own data set from this. In the case where maybe the traditional train test split doesn't work in this case, but we can build our own splits based on our data frame. Next, I am using the pipeline method in order to stack together our standard scaler. So now we're going to Z-scale the entire data set. We are going to perform PCA analysis and return this as a data frame, but we're going to fit the data just on our X train. So recall X train is just the lab portion of our data set. And so we're not building the PCA model on all of the data. However, we will transform all the data and look at that impact on the scores scatter plot. And so here we have our pipeline. You see we have our standard scalar and PCA that is generated from this line here. And in the following line, we're transforming all of the data. So we're going back to X. Now, this is the same as if we were to run pipeline.transform xtrain and then pipeline.transform xtest. This is just an easier way because the key step is not fitting on all of the data, but just the xtrain data. If you want to verify that, you can modify the code to do so, but that is indeed the case. The model parameters are just being fit on the training data set, which again is this lab data here. And then our convert columns just allows us to have our columns be called PC1, PC2, PC3. So here is where we can actually see the impact of our analytical data. When we run this and we compare our lab data and our other data, we can see that they don't overlap very well. There are some artifacts in this sensor. There are some other things we might need to do, but a couple of notable things. One, the shape of the data has completely changed. Recall, we've looked at the PCA of this data set, and if we were to go back and look here, the PCA has this sort of center point and then has these spikes due to the various impurities known in the data set. Again, we've looked at this a number of different ways, but there are many impurities that we know to exist in this data set. So we are still expecting this sort of outward expansion of our data set, which is not existent anymore with the SCiO data, and largely because we're looking at a relatively small wavelength range of the data. And here perhaps is where there isn't much information there, at least relevant to that original pattern. But however, one thing that's more notable as we think about how we handle in situ versus in-lab data, the data sets don't overlap particularly well. And there are ways that we can actually measure this distance between the centroid of our lab data versus the centroid of our, in this case, the SCiO instrument. And so one other thing we want to do is go back and actually apply our hoteling t-squared. So that was what we did in part 1.5. And we're using the same plot confidence ellipse. Again, we cover that in this video here. And we can see, based on our 95% confidence ellipse, that these truly are different pieces of data. And perhaps if we're trying to build a model where we want some congruence between the lab data and the other data, this might not be the best source if we have options of exploring different instruments, which in this case we do. However, that's not to say that this is not usable data, but it does pose an interesting challenge as we think about our data set. And so one thing we might want to consider is measuring the distance between the lab data. And we can do that using the distance module. So this is imported from scipy.spatial. And let's say we want to compute the Euclidean distance. A couple of variables that we can use are mean scores 1 and mean scores 2. So these would be the respective score values for PC1, PC2 for each group. And so let's look at that before I run that calculation. So if we look at mean scores 1, we see we have our two PC values that are pretty close to 0. That is this blue region there. And then if we look at mean scores 2, that is, PC1 of 29 and PC2 of 13. So that is this other orange region there. And so we actually can compute the Euclidean distance between these 2 points. And so this would essentially be that straight line distance between the centroid value here and the centroid value there. And we can simply just pass in mean scores 1 and mean scores 2. And we have a Euclidean distance of 32. And so let's save that here, actually. Let's make a dictionary called NIR dist, and we'll say SCiO, and the value for SCiO is 32. We'll just round that to 0 decimal places. And as we add new instruments, we will add them to our dictionary. And so if we go back to the top of our list here, all we've got to do is just change this to a different source. And so we can look at the MicroNIR and see all of the changes. Again, fname here, the other path is automatically updated. This is taking in this fname.value. We run this and we look at that lab df is not changed. So I will now switch this to other df, and we can see that now we have a different wavelength range between 900 and 1676. One of the other interesting features is that we don't have a measurement at each wavelength. We actually have what looks to be a resolution of about 6 nanometers. Again, this is one of those common trade-offs when you have a miniaturized instrument. And thus, when we do our concatenation, our resulting data frame is this concatenated data frame with whichever data frame is more restrictive. In this case, continues to be the other. And so we're only looking at the wavelengths that overlap between the two data sets. If we run this all the way down to the bottom, we can see in this case that we have significantly more overlap as we, again, run our PCA model and fit it on just the lab data and then transform all of the data. And if we look at the hoteling, we can see that we have much more overlap between our two confidence ellipses. And visually, again, we can see that they are more similar. If we measure the distance between the two, we have a much smaller distance. And so we are looking at, I believe, micro, and we have a distance of, let's say, 0.5. Let's verify that that was the right instrument. Yes. Okay. And so if we switch to our last instrument, the NeoSpectra, run this as we have before, all the way down. We have a different wavelength range. We have 1299 with a bandwidth of 4 nanometers, or wavelength resolution of 4 nanometers, all the way out to 2600 nanometers. We look the affected all data, and we refit our variables, run our model again, see that we, in this case, have even more overlap. So there's a lot of information in those large wavelengths that really correspond to the underlying structure of that data. If we, again, look at the hoteling t-squared, we see we have almost complete overlap, especially around the centroid of each of these regions. And if you measure the Euclidean distance, again, it's also really small. And so in this case, we might say that the NeoSpectra and the other would be a really good one-for-one instrument when comparing the outputs from our in-lab measurement and our out-of-lab measurement. And that's not to say that we can't do more with this, but this is just one way to assess the data. Now, it could turn out that for other reasons, we actually need to try to figure out how to get the SCiO data set to work better and the instruments to work better. And thus, we could actually build models that might allow us to predict based on this. And in fact, one of the publications did do that. But this is just one way to see how we can take in-lab high-quality measurements and attempt to translate that into a portable instrument device. And so I hope this video was helpful. I hope it allowed you to see how we can take a lot of the understanding that we've made in the previous videos and translate it to what might be a real-life scenario. I'll continue to explore this data set to see what else we can do with it, but I hope now your imagination is further provoked as we look at this from various different angles. In the case, I see you in the next video. Peace.